Today we're going to talk about future value annuities. So far what we've talked about is either borrowing one chunk of money that we pay back at the end or investing one lump sum of money into an account and letting it sit. We haven't talked about the situation where we withdraw money or we add more money to it other than interest. So we'll start with our definition of what an annuity is. An annuity is a financial plan characterized by regular payments. So the first thing we'll talk about is ordinary annuities. So let's suppose we invest $100 into a bank account at 5% interest compounded monthly. In January, we would have $100. But in February, we've earned about 43 cents of interest on that $100. But then we're also going to put another $100 in. So now we have the $100 we started with, the $100 we just put in, plus the 43 cents that we earned in interest. So now in February, our account has $200.43. So in March, we've earned roughly 89 cents. So by the end of March, we put in another $100. We have that extra interest payment. Now we have $301.32. So if we continue to add $100 every month, it's no longer a simple investment. Now we have what's called an ordinary annuity. So here's the formula for finding and calculating the future value of an ordinary annuity. We have S equals R times, and all of this is in parentheses, this big thing, 1 plus I raised to the n minus 1 all over I. So now let me break down the components for you. S is still future value as it has been. R is the continual investment. This is the amount of money that you put into your bank account every month. I is the interest rate per period. Now you have to calculate this by taking R divided by M. R is the interest rate, which we've seen before, and M is the number of compounds, which again we've seen before. And then N is the number of investment periods total, found by M, which is still the number of compounds, times T, which is time, and again that's usually in years. So when we solve an ordinary annuity, what we want to do is find each of the components of the known variables and solve for the unknown variable. So for example, let's find the future value of an ordinary annuity if we pay $80 every quarter for 3 years and we get an 8% interest rate compounded quarterly. So let's first find the components. R, the amount that we invest on every period, is 80. I, which is found R divided by M, we turn our percent into a decimal, so 0.08 divided by 4, which gives us 0.02. And then N, which is M times T, 4 times 3 gives us 12. So now we have our ordinary annuity formula, future value, and we plug in all of our knowns. Now take your time when you're doing these calculations. Do any basic simplifications first. This is pretty easy to do right here, the 1 plus 0.02. And then slowly go through this. If you try to put too much in your calculator and you don't put parentheses in the right place, you're going to make mistakes in your calculation. So I'm going to take the 1.02 and raise it to the 12th power first. Get that taken care of. Just like we've talked about before, we're going to save all of our rounding for the end. Now I'll subtract the 1 in the numerator. Now I'll take these two values and divide them, and now I can multiply and distribute that 80. And we get S equals 1,072.967178. Now we're at the end, so now we can do our rounding. Future value is money, so we measure that in dollars and cents. So the future value of this account will be approximately $1,072.97. Let's do another one. Let's say that we take $2,500 and deposit that at the end of each quarter into an account that earns 5% interest compounded quarterly. How many years will it take for the account to grow to $80,000? So what are we looking for here? We're looking for time. So let's break down into all our different components. We want the account to grow to $80,000, so we want S, the future value, to be $80,000. Our continual payments that we make is $2,500. We can find I, our interest rate divided by our number of compounds, which gives us 0.0125. And now N, the number of payments, periods that we have total, is M, which we know is 4 times T, that's our unknown. So now let's plug all those values in and pay close attention to where our unknown variable is. It's up in the exponent. So now again, we're going to do all of our basic simplifications. Everything we can do first, we can combine these two numbers together. So now we need to get t by itself. We're going to work the furthest away from t. The last thing you would do in your order of operations is the first thing you're going to get rid of. So we'll start by dividing both sides by 2,500. And now we're going to get rid of this 0.125 by multiplying both sides. Now we can add 1 to both sides, and we get 1.4 is equal to 1.0125 to the 4t. So now the variable, the unknown that we're looking for, is stuck up in the exponent. So we need to bring that exponent down somehow. So we have to think back to what we've learned that can help us bring an exponent down. And I hope you're thinking about the properties of logarithms. Remember, you can do whatever you want to an equation as long as you do it to both sides. So what if we were to take the natural log of both sides? Natural log being one of the more common logarithms we have. So whatever we did to the left-hand side, we did to the right-hand side. But notice what you're taking the logarithm of is all being raised to a power. So now we can bring this power out front and make it a coefficient. Now it's just a regular algebraic problem to solve. To get t by itself, well, this is 4 times t times the natural log of 1.0125. So we can divide both sides by the 4 and the natural log of 1.0125. And this is something you can put in your calculator. Just make sure when you do the natural log of 1.4 divided, you put the 4 times the natural log of 1.0125 all in parentheses. And when you do, you get 6.7714166682 is t. So you would say that this is going to take you approximately 6.77 years for this to grow to about $80,000. Okay, here's one more definition for this section. This is called annuities due. Rent payments and insurance premiums are examples of annuities due. Unlike ordinary annuities, the annuity due has a periodic payment made at the beginning of the period. So the term of an annuity due is from the first payment to the end of the one period after the last payment. So what does this mean? This means that an annuity due draws one more interest payment. It's going to draw interest from one more period than an ordinary annuity. So the key word here to know it's an annuity due and not an ordinary annuity is the word beginning. So the formula for the future value of an annuity due is going to look just like the formula for an ordinary annuity, but we tack on this one extra interest payment here, that 1 plus I. S is still your future value, R is still the continual investment, I is still the interest rate per period found by R divided by M, where R is the interest rate and M is the number of compounds. And N is still the number of investment periods found by M times T. M is still the number of compounds, and T is your time, usually in years. So let's do an example. Find the future value if we take $150 and deposit that into an account at the beginning of each month for 9 years. And the interest rate is 7.2% compounded monthly. Okay, so the key word here is beginning. So let's find our components. R, how much we're investing, is $150. I, R over M, we're compounding this monthly, so 0.072 divided by 12. And then N equals M times T, number of compounds is 12, times the number of years is 9. Now the key word being beginning, because we're doing this at the beginning of every month, means it's an annuity due. So we have to tack on this one extra interest payment. If you don't see the word beginning or nothing that alludes to when during the period you're going to give it, it's an ordinary annuity. But anytime you see that word that you're going to do it at the beginning of the period, beginning of the month, beginning of the year, beginning of the quarter, beginning of the whatever, the day, then you know it's an annuity due and you need to add that 1 plus I at the end. So plug in all of our components. Again, we're going to do our basic simplifications. Make your calculator do as little work at the end as possible. We can add this 1 plus 0.006 on both of these pretty simplistically. Now we'll calculate this numerator first. Don't try to put too much in your calculator at one time. So if we take the 1.006 to the 108th power and subtract 1, we get this big long decimal. And again, save your decimal rounding for the end. Now we can divide these two values. And now we have 150 times 151.3359308 times 1.006. That gives us that one extra interest payment right there. Calculate that all together, we get $22,836.59196. So the future value of this account will be approximately $22,836.59. That's it for now. See you next time.